Good afternoon, friends. Today's 13th lecture will be taken, as you can see, Dr. Shraddha Desai. Before the module on neutron diffraction begins, is a single lecture on neutron detectors. I felt it is justified that you learn a little bit about neutron detectors, and Dr. Desai is an expert on making various kinds of neutron detectors, which is at the core, at the heart of the instrument that we build. So I will leave it to Dr. Desai to tell you the fascinating story of various detectors and how they are used in neutron diffraction. Dr. Desai.
Hello. Thank you, Dr. Basu, for kind introduction and welcome all of you in this classroom. So, for I understand last few lectures you have been learning about new properties of neutron and how neutron can be used for various. So, it's important that we learn how it is detected. Wherever the neutron is, whether it is coming from the reactor or it is coming from other fusion sources, and it is used on the sample and it is scattered from the sample, at every stage you will need a detector. So these detectors are of various types, and today I'm introducing you to the basic principle, how they are detected, how they are, what are the properties of the detector are essential for our neutron scattering experiments, and how this nuclear reaction for a neutron detection can be used for using a one-dimensional and two-dimensional. So just a brief introduction. So just the outline of my talk will be like there are various radiation detectors like alpha, beta, gamma, and neutron. So what is the basic difference between other radiations and neutrons? How they are handled, since their interaction with matter is not like other charged particles, so they have to be handled differently. So these radiation detectors are also varying from the principle of their interaction with the matter. So either scintillation or gas field detectors. So gas field detectors have some advantage. So we will be using these gas field detectors for all the neutron. We'll be using for this all neutron scattering experiments, and all the detectors which are used right from the beam monitor right to the scattered and neutron scattering ends of this experiment. So all these detectors, how they are being varying in the principle and operation, like their hardware, it has been changing, the neutron count rate capability. So all these properties of neutrons like efficiency, sensitivity, how they are determined, and how we use these properties for a specific tailor-made application at a neutron scatter. So how is a counting detector is different from position sensitive detectors? Then position sensing, there are various methods like charge division, delay line methods. So I will just introduce you all to a different, uh, entirely like it is physics plus mechanical engineering and electronics. So combinedly, we will just see how these neutron detectors are getting evolved through the procedures. So this is a one-sided view of a Dhruva reactor. You can see all these beams are coming along from beams are taken, then with the monochromatic drums. Yeah, I'll just. Okay. So now you can just see that these are all neutron beam holes, and these are other.
You can see the pin moving. You can show the pin moving.
Okay. Okay. Yeah, so beams coming from reactor, they are being used here, and this they are passing through a monochromator and okay. So these are the monochromated drums. So after coming from a sample, this monochromatic drum is falling on the sample position, and so once it is scattered, there are various detectors lying over in this shielding. So you can come to. I will show you in detail in the later slides. So this is just to give you idea like how uh, this all this react. So how all these instruments are equipped with the in-house made neutron detectors right from a beam monitor till the scatterings. So these are the usual applications of the other radiation detectors you have been seeing in day-to-day life, like from right from the medical imaging for simple X-ray, MRI, PET scans, and so these are all using a different functions for the different radiations. So, but now we will concentrate on the neutrons today. This is one of the security portal monitor and that is security in case there are some any radioactive explosive are being carried. So they can be just detected at the security ports. And this is the nuclear industry where for even for the reactor operation like in-core, out-of-core and beam monitors. So all these type of detectors are needed wherever any radiation is available. So radiations are of various types. So alpha, beta, they are being detected through ionization. X-rays and gamma rays have some basic interaction properties like the photoelectrons are emitted, Compton scattering, and a pair production in which you must be very familiar. So here in case of neutron things are very different as it is not interacting with any, not just any matter but with very few matters it is carrying out a nuclear reaction like neutron absorption reaction and that is the principle which is used for the exothermic nuclear reaction is used for detecting this. So secondary charge particles resulting from the neutron interaction are used for are indirectly used for the neutron detection. So there are among various other interactions. One is the ionizing the gas medium, scintillation here, where the direct ionization is not possible. Here it is excitation and de-excitation is also carried out, so that is exciting de-excitation photons are being detected, and that is indirectly scintillation detectors are used. In case of semiconductor detectors, you have a reverse bias NP junction where the incoming radiation create a bunch of electron hole pairs and these are been creating a pulse which is a recordable pulse and which is representing a radiation. So in case of scintillation detectors, you need a crystal in which incident radiation is creating a visible photon. So this photon or a bunch of photon is passed through a photocathode which is creating a bunch of electrons and this further bunch of electrons is further amplified to get a considerable signal to noise ratio and this pulse represents the energy of incident radiation, that is the principle of scintillation detector. But as we see here, we need a perfect crystal for this purpose. And in case of neutron, we will be having a lot of gamma sensitivity also carrying with this crystal. So, as such, for the today's topic, wherever we are considering neutron to be detected, which is always accompanied by gamma, so gas field detectors are always of more importance. So here these are semiconductor detectors. As I say, a NP junction is treated with the reverse bias and in this depletion mode, whenever radiations are falling, so you get the electron hole pairs. So these pairs are contributing to the pulse. But as at the same time, you know that silicon wafers have a limitations on the size. So this can be of the size of the chip or IC. So whenever we are needing to have a neutron detection, or further your detection area is quite large as in the meters, so these semiconductor detectors have lot of limitations on the size. So in that case we have to go for a gas field detectors. So here whenever we have a detector, whatever output we are getting output from it, it can give us three different type of informations. Either it can reflect the complete energy of the incident radiation, which is only possible for direct ionizing detectors or photoelectric effect like using for X-ray or gamma, but not for neutrons. Counters means it counts only the number of interactions or number of incoming radiations falling on the detector, whereas dosimeters, which are mostly used for this health physics and other experimental purpose, the total net amount of energy which is deposited in the detector volume. So, for example, if you would like to find how radiations are affecting a human tissues, so in that case, the detector material will be of the tissue equivalent material, and in that case, we can directly get the net amount of energy that can be deposited in the human body itself. So such detectors are called as dosimeters. So now, as I have told you, the advantages of using gas field detectors, because gas field detectors can be made of any size desirable, and we can just tailor the hardware of it. So in that case, we have to start from how the electrode or how the pulse are formed within the gas field detector. So you can just have a two electrodes. Either it can be coaxial just for some convenience. And in that case, when you are applying high voltage to the anode and the cathode is mostly grounded. So the ionization taking place between these two electrodes give rise to a voltage or current pulse, and that pulse is later processed through the preamplifier and amplifier circuit. So the incoming radiations are creating the ionization ion pairs. All these ion pairs, bunch of ion pairs are traveling towards the anode, as there is a voltage applied between two electrodes, and these electrodes collect the charge to create a pulse which is resulting from the radiation. So when we are having two electrodes and you have a bunch of electron and positive ion pairs, these all charge cloud can be treated by applying a different voltage. So the electric field created within these two electrodes can vary. So how, when we are varying the electric field within this by increasing the voltage, the collection probability of all these ions or charge changes. So in the initial stage, when your electric field is not very high, there can be some recombination, but that recombination is slowly suppressed by increased electric field. And here a stage arrives when my problem. Okay. Okay. So, hello. Ah, okay. Sorry for the disturbance. Here, when entire charge cloud is been collected at a certain point, here recombination is suppressed, and we are reaching here for the ionization region. So your ions charge collected and charge created is same. So that is the reason where this region is called as ionization region. So when voltage is increased beyond certain stage, we are reaching here for the avalanche formation. The electric field between the electrodes is so considerably high that these electrons are accelerated to form a secondary electrons, that is, and this avalanche is created till your anode is reached. That is why your number of electron hole pairs are getting multiplied, and this multiplied is by a specific number. That number is called as an amplification factor of the detector. So by amplifying this charge, we are considering this charge as a signal much beyond the noise. So your amplification reduces the constraints on your external electronics to see the signal pulse. So this is called as a proportional region. You are still having amplified pulse, but your amplification has a direct proportion to the incident radiation or the incident initial charge created in the detector volume. So this, by increasing the voltage, there is up to certain region it is keeping it proportional, whereas beyond certain electric field, your amplification increases so high, the charge cloud is so high that space charge is created. So when a space charge is created, your electric field deflects, and it is not anymore proportional to the incident radiation. So beyond certain voltage, again, uh, the avalanche is such a created that any amount of initial charge is uh, it is a self-limiting process. So any amount of initial charge will give you the entirely same amplitude of the output pulse. So these are like 4-5 regions of the operation when we are having a detection volume in the detection volume. But now for our convenience, for the signal to for a good signal to noise ratio, for a good gamma discrimination, we will be using this proportional region for our other detector use. So how a very high charge can be created when you have parallel plates? Your formula is just V by D, but in that case voltage needed is extremely high. So just to have a very high charge within near the anode, so you can select a very small anode, very thin wire as an anode. So as long as we are going very close to R, very close to anode surface, when R is reduced to in microns, your electric field shoots up quite high. And this electric field high beyond certain critical voltage, electric field, it helps in creating the avalanche. So this is just a pictorial form. So you can just see this, yeah. So all this charge cloud which I am showing here, this is created in very small vicinity of wire. If wire is 25 micron, you can just see that within 10 to 20 diameters of the wire, like within 200 microns of the area, all this charge is been created. So around the wire, so entirely on the other, completely whenever your wire is surrounded by this charge cloud, it is facing the very high electric field. Multiplication is carried out, and after multiplication, whatever charge is created is been processed by the electrons. So this is the principle of proportional region, where your initial charge is amplified internally. Okay, so here you can see this, how a detector is actually a simple counting detector, how it is made. It is so rugged that you can have a very tough outer casing and a very thin anode here. It helps in reaching a very high electric field, but handling this anode wires is also a very skillful job. So you can choose like 25 micron, 10 micron as per the requirement. So this wire thickness determines the operating voltage of the detector. So you have a casing, a very thin wire, and a gas field in this detector can give a simple hardware of the detector structure. Okay, so now this exact symmetry, how wire should be exactly axially symmetric at the center of the cylinder. There shouldn't be any sagging and all these properties. They should not have any impurities in the gas. Metal should be very clean. All these are the properties which make your detector very durable and simple, so that it can be used for years together. So just a pictorial example how a charge is created. We can just have a look. Like here, neutron, I'll just call is neutron, but it is valid for any type of radiation. A radiation comes and the primary charge is created. How a primary charge is created? You have E as the energy of incoming radiation or a charged particle, and there is a fixed W value, like energy needed for creating one ion pair, that is a W value. So the total number of ion pairs, the number of electrons or positive ions created are depending on your energy, incident energy. So N naught E is a primary charge cloud. So here in the, when it is drifting under the effect of electric field, it is drifting quite close to anode, and while drifting towards the anode, the number remains the same. When very close to anode, during the critical electric field, it is amplified. So you can just see that here M is a gas gain. So this is the amplification factor of this detector. It depends on what is the amount of electric field you are applying between these two electrodes. So the voltage pulse which we are collecting at the output, it is like this charge is collected on the capacitor, feedback capacitance of the preamplifier. So this is the actually voltage pulse which we are going to receive at our output end. Which is proportional to N naught. And this N naught is nothing but the incident energy. It is reflecting the incident energy. Okay, so now just let us take one helium-3 NP, though I have not come to neutron absorption reaction, just to make you convenient, like how your voltage output is proportional to your initial ionization created in the gas. Helium-3 has a neutron absorption cross section, high absorption cross section. So NPT reaction, like after absorbing neutron, it will give proton and triton and plus the Q energy of 764 keV. So average for creation of one ion pair, you take it for, it is different for every gas, but we take an average value here. So 764 keV by 30 EV for one ion pair. So in this case, initial charge cloud created is just 25,000 ion pairs. This is a primary charge cloud, and our internal amplification will amplify it to further. Whereas in case of boron 10 in the BF3 gas, the reaction absorption reaction is N alpha, and the Q energy of boron and N alpha reaction is 2.3 MeV. So here see the Q reaction is very high. So in that case here again we take 30 EV as number of electron as a work function. We get 75,000 ion pairs for the same single one neutron. It depends on like what is the Q energy of our interaction. So this contributes to the primary ion pairs of the detector, and further it is amplified. So now coming to neutron, as you must have studied before, that it doesn't interact with all the atoms. Being a neutral particle, it can pass through various even meters of stainless steel without interacting. So there are very few isotopes where neutron has a nuclear reaction, and this using this nuclear reaction we can detect them. So helium-3 and BF3 are only two materials which are available in the gaseous form. Again, boron 10, elemental boron 10 also can be available in the solid, so the coatings can be used. So these two are very these are our candidates for using them in the gas filled proportional counters. Whereas going for a lithium, yes, it has a very good Q value, so gamma discrimination is possible, but its absorption cross section, though it is low, it is a very highly hygroscopic, and we have to make a very good crystals out of it for and these hygroscopic crystals have to be handled very carefully. So the lithium can be used mostly in the scintillation detectors. Now uranium, again it is uranium 235, can be a coated one, has again a very low absorption cross section, but these are again the solid coatings which are usually used in the fission chambers. Here gadolinium 157, this isotope has a very high cross section, so we may think why not use this. But you can just go through the secondary continuum beta output, which is having a continuum up to 182 keV. So here gamma discrimination is not possible and this Q energy is quite low. So this can be used only for imaging screens and coils. So here we will concentrate more on only helium-3 and boron-10 reactions. So when the neutron is captured using these two reactions, we can just see that the Q energy is released, as well as in boron 10 you can have electromagnetic energy or excitation energy in scintillators. So all these things, they will have some probability of reaction to occur, and this probability of occurring is called as a neutron capture cross section. So this capture cross section, which you have seen in the previous slides, I have given here the number. So now I'm explaining what exactly it is. So this capture cross section is a probability, and it is measured as a surface area which is available for the reaction, and it is so small. It is, though it is in 10 raised to minus 28 meters square. So this a unit given to it is in bands, and this cross section reduces with the increasing velocity of the neutrons. So a neutron with 1 eV or a thermal neutron, so anywhere if you have a same detector and if your neutron energy varies, your number of counts which you are getting out of the detector will be different, and this is where it is reflecting from the absorption cross section. So here I'm just showing you how absorption cross section varies. So in case of here, this is of our application. So I can just show you. These are due for helium-3 and BF3, helium and boron 10. So here, this is our application range is from 10 raised to minus 3 to 10 raised to minus 2. So in that case, these are absolutely linear. Here at a very high neutron energy, there are some resonances seen, but we are not reaching there for right now. So what we get here is your neutron absorption cross section reduces with the increasing neutron energy, and that is how we have to consider the neutron energy or neutron wavelength when we are designing any detector as such. Is this appearing? Okay. So neutron absorption reaction. Now we will study the helium-3 and neutron absorption reaction slightly in a detail. So as I have told you, it is a NP-T reaction. So on a neutron absorption with the helium-3, a proton and a triton are emitted, and this is a Q energy of the reaction. So 764 keV is a Q energy. It is distributed in these two charged particles, and it is gained as a kinetic energy of the charged particles. So this proton and triton are released in the gas, and these are what are ionizing our gas medium. So charge pairs or ion pairs which are created are not due to direct neutron, but these are through the proton and triton, which are when having energetic proton and triton released in the gas medium. So these ion pairs which are created with this proton and triton are again, as I told you before, they are been drifting towards the anode and they create a pulse. So here I am showing you a pulsate spectrum of the neutron detector, which is having helium-3 as a neutron absorbent. So helium-3 results into a detector pulse output, which is showing as a 764 keV. Just to caution you, this is not a neutron energy, but this is energy of the reaction, Q reaction, because the charged particle which are creating ionization are of 764 keV. So in neutron detectors, whatever pulse we are getting is representing the energy 764 keV. So here a total area under the pulsate spectrum is showing only number of neutrons detected. So here indirectly it is a neutron counter and not an energy spectrometer. So this many times while looking at the X-ray and neutron detector, there is a confusion like if whether this energy we are seeing is of the neutron. And here I am showing one small factor as a FWHM. It is a full width half maximum. So here this is one of the property. It is showing that all our pulses created due to one helium-3 neutron interaction are nearly giving us the same amplitude. They are giving us the same M, that is same amplification factor, and this is where our completely completely symmetry of the detector and a perfect including hardware symmetry as well as a gas purity is reflected here in a very good pulside distribution of a detector. So this is one of the basic requirement that your detector should give a very good pulside distribution. It means it is been prepared well. So the pulside distribution uh, okay, it's the same reaction, just shown in slightly different form. So as the kinetic energy distributed between proton and triton. So here peak position is equivalent to the 764 kV of Q value of the reaction. And here specifically I am showing you two small harms. These are if this reaction does not take place entirely within the gas volume, if there is a partial collection, then there are these two wall effects which are specifically showing peak at 191 kV and another one is 564 kV, that is for the proton peak. So here and all the gamma pulses are discriminated below a certain noise level. So this good pulsate spectrum can give us the advantage of discriminating gamma and other electronic noise pulses as well. So this is a similar reaction for boron 10, but you can see here there are two different reactions because this nuclear reaction of boron 10 and neutron has a branching ratio because when out of every 100 reactions taking place, the 94 of the reactions will be having a ground excited state reaction giving this energy and others will be a ground state reaction. So this majority is 2.31 MeV. So we just have the calculation here like how the energy 2.31 MeV is distributed between lithium and alpha particle. So this energy of 102 and 178 MeV is again reflecting here. You can see this pulsate spectrum of the peak 2.31 MeV and this pulse, this spectrum. Okay. Sorry, here this peak is 2.31 MeV peak and this other one is 2.7 at the ground state peak. So in that case, where is the energy difference going between 2.78 and 2.31? Is there is a small 8.8 MeV of sorry of 0.48 MeV of a gamma is been emitted on de-excitation uh, of this lithium particle. So this is how a boron 10, a BF3 boron from BF3 gas will show us the pulsite spectrum of the detector. So again, similarly, what we saw was the gaseous form of boron, but when we have a boron coating on a substrate and reaction takes place in the solid converter. So when you have a boron layer, we can just see that here a neutron interaction takes place and a lithium and alpha particle release. They are traveling through the solid as well as entering the gas medium. We have a cylinder in which inner side is coated with boron 10. So in that case, one of the particle is lost, whereas other particle is partially absorbed in the solid medium and still it is released in the gas medium. So this ionization is created and showing a pulse. So pulse height of solid boron there is slightly different from our BF3 gas. But in certain case when where we don't want to use gas medium, in that case the boron solid boron coatings can be used in case of certain detectors. Okay. So now you have seen how structure and the operation of the detector is taking place. So now we come to the properties of detectors. So the first property of the detector is detector sensitivity. It means we have made a detector of a certain amplitude, of a certain dimensions, filled a gas at certain pressure. So now when we keep it in the ocean of neutrons, suppose a unit neutron flux, a flooding neutron, how many pulses it will give? That obviously depends on this absorption cross section as a velocity of neutrons, as we have seen earlier, but the overall sensitivity is calculated by using n. Here is a total neutron sensitive material, number of neutron sensitive atoms per unit volume. This is the total volume of detector and in which the gas is filled, and this is the neutron cross section. So just for the cross section is taken at the mean velocity. So 1.128 is a normalizing factor. So you can see here how many counts we are getting from a detector when kept in unit neutron flux. It is a volumetric property of the detector. So entire detector volume should be placed in the ocean of neutrons. So here this property is useful for determining the total counts, how we can get how much of the neutron flux we can expose to this detector before it reaches the saturation, or till it gives a good number of neutrons which are beyond any noise level or beyond any background level. So that is how we have to design the sensitivity of the detector beforehand so that it's a neutron flux of interest for a particular experiment can be determined. Okay, so this counted capability is maximum number of counts which detector can give. It also has a role from a dead time of the detector or the time needed for processing a single pulse of the detector. Okay, the other important property of the detector is detection efficiency. So this is again a ratio of number of detected neutrons to the total number of incident neutrons on the detector. And again you can see here there is no volume coming into this picture. It is 1 minus e raised to minus n sigma t. Again n is the same number of neutron sensitive at nucleus or material per unit volume, and sigma is a neutron cross section, absorption cross section, and T, here T is a thickness, gas thickness through which a neutrons is passing, or it is a thickness of the detector from which we are incidenting neutrons. So here it is a directional property and not the volumetric property. as we have seen for sensitivity. So for each detector, sensitivity and efficiency can be, they are very different, and they are being considered, both are important. They are being considered for what way we are going to use the detector. If it is used for area monitoring, yes, sensitivity is important. But for neutron scattering application, when we have a neutron beam and a neutrons coming from a particular direction, in that case, efficiency is more of the consideration. So suppose we have a small cylindrical detector. So it same detector can show us two different efficiency values. It depends on in which direction we are using. Suppose if we are using in the radial direction, like one edge of the detector, a circular edge of the detector incident with the neutron. So the distance traveled by a neutron in the detector volume is along the chord. Like this I have considered because this is the biggest chord along the diameter. If it is here, then it can show a smaller chord. So in this direction, when the neutrons are incident, T varies here as per from diameter to the smaller values, whereas a detector is mount in the end on position, like it is facing the circular, uh, if it is coming from the flat portion of the cylinder, then you are seeing the entire length of detector as a T. But here it works as a point detector, and here it works as a linear detector. So that is the difference. When you want to use it as a point detector, use it in the end on position, or if it is a linear long detector, then you have to cover larger length, then it is a side on position, but the efficiency is a factor which has to be considered. So here, just for a easy, just to make it easy for calibration, here a generalized graph is plotted here, considering this A is Armstrong, that is a neutron wavelength, pressure, gas pressure, and centimeter is a T, that is thickness. For helium 3 and BF3, this is just for a comparison, it has been plotted together. So if you want to get a efficiency nearing beyond 80 to 90%, then your X factor should be exceeding 45 to 50%, so you get the most efficient. Here we can see that BF3 is anyway having a smaller neutron absorption cross section, plus there is another constraint on filling it at the high pressure. So for efficiency, higher efficiency, helium-3, which can be filled at any atmospheric pressure, helium-3 is the best option for it, but cost is the another issue. So after this neutron interaction and other neutron detector properties, we'll just come to how a pulse is formed in the detector. So as you have seen, the charge cloud which is coming closer to the anode is creating a pulse, and it is creating a voltage, charge to voltage converter, which has been taken by this charge sensitive preamplifier. So in a feedback loop of a preamplifier, we have a capacitance as well as a RF resistance. This takes care of the noise constraint, and charge which is integrated on the feedback capacitor flows through this RF so that your pulse is amplified, and it has a finite timing for which your detector is being dead to the second neutron incident pulse. So this is determined by a feedback loop, and further the same same pulse which is having a finite rise time and fall time is passed through a high pass low pass filter for a noise suppression and converting it into the Gaussian pulse. So this is how electronically a pulse, neutron pulse, is processed in the external circuitry of the preamplifier and amplifier chain. So this is just a small picture of how we can see this is a counting detector. This is this 30 centimeter long neutron counting detector, usually used for neutron monitoring, and electronic supporting electronic. Just to give you idea how we have seen the block diagram, this box is a preamplifier in which a voltage is also HV is also is applied through this, and the detector uh, it goes through the detector, and the output of the preamplifier is given to the spectroscopic amplifier, and after having a particular settings of the time constant selection, gain selection, you can get a very good pulse for this from the neutrons. So here you have a counter scale. So number of neutron pulses created in the detector circuitry are been plotted here. As we go on increasing the voltage anode bias, you can see that you reach a flat portion of number of counts. What we saw before was a pulse height distribution. It is like a picture of how big the pulse height is. And here, whereas you are integrating all the pulses, so what you get is a number of pulses. So that is the total peak area under that curve of a PHA is what is plotted here. And this flat portion of these two different detectors which I am showing you is treated as a point of safe operation, so that any deviation in the EHT or HV cannot give you a false counting around here plateau region. So this is another property of a detector which is essential. So it should show a flat portion of the operating anode bias, so that it is a you can have a good selection of the stable operating parameters. Okay, so this is just a schematic of spectrometer which you are going to study in the latter lectures in detail. Just to give you a idea, when you have a beam from from a reactor, it is a polychromatic. It will have some just a very average shape. And for a particular experiment, we are choosing only a small slot of it, so that we choose a small delta lambda which is of our interest. So here you can see at the first stage of monochromatization itself, we are having a considerable reduction in neutron intensity, but this is useful for giving a very good resolution for at the output. So this monochromatic beam is falling on the sample, but before that you should have one neutron monitor counter which will give you a quantification like how many neutrons are falling on the sample. So the first detector using a detector starts at this stage. So this normalizes also any variation in your output. How many like from the beam, any variation in the reactor power is also reflected in this, and so number of neutrons falling on the sample are been confirmed. So here when the scattered neutrons you are trying to detect, there are three different ways. You can use the detectors of three different geometries. Either you can use a simple point detector as I have shown before in the end on position, and then this detector can scan the entire area of interest. But this experiment takes quite a long, and at this, as the reactor neutrons are very costly, the reactor operation from reactor operation side, if we want to complete our experiment in reasonable time, though this is a very stable and good process, this experiment runs on for days together. So just to reduce the experimental time, if you use a position sensitive detector, it can cover an area of interest within linear range. So you have a long cylinder, and now this detector, position sensitive detector, will give you number of neutrons as well as the position at which the neutrons are falling. So you get n as well as x, that is a position. So this again covers only a small line of the total pattern from a scattered pattern from which you want to test. Here, two-dimensional PSD, that is the area PSD, can give you the entire volume within the very short time. So this area detector, but again has a very complicated, as you can see from the dimensions itself, a complicated hardware structure as well as a complex electronics for processing the pulses, which I will just slowly brief you. So how to convert a simple counting detector to a position sensitive detector? So when we were using a thin wire in the simple cylindrical detector, uh, it was a single way output and there was no resistance in this wire. So we were integrating all the neutrons falling in the total sensitive area. Whereas now for position sensitive detector, we can use this resistive anode. For resistive anode, for a metallic anode, it has to be still thinner because, as you know, specific resistivity reduces by the area, cross-sectional area of wire. So you use nearly 10 micron of wire, either nichrome, and it should be stretched at the number of as the length of the detector needed, and then take the pulses from both the ends and process them in such a way as a potential divider. So in that case, when your output is taken from both the ends and the position sensitive detector gives you different positions, and that is reflecting as a different scattering angle of your interest. So here the entire work is done faster. So here itself our 3 days experiment can reduce to few 3 to 4 hours of the experiment. That is the advantage in getting a position sensitive detector. So how position sensitive detector works, I will just show you a small expression for it. Here, when you are having an incident neutron, a charge cloud is created here. So charge cloud is created around a point of interaction. There is a charge cloud is projected on the anode wire, and then it has a distribution of the charge. So here in the direction of A and B, your charge is divided. So that is why we call as a charge division position encoding. When our charge is divided, we are receiving different output voltages at both the ends, and this is the way they are processed. So output at the VA is varying from the output as VB because of the position difference, and this position difference when processed, these two pulse amplitudes when processed through a VB upon VA plus VB gives you a output which is proportional to position. So that is this X can be measured through a position encoding of charge division. So here there are other conditions like you should have a very equal gains in both the branches. Your preamplifier input impedance should be very low because we are having this assumption as Z is very much smaller than as compared to the total resistance of this detector. So in that case, uh, our position encoding is through a very specific electronics. Care is to be taken that our gains are perfectly matching in both the branches. So here again this summing amplifier and ratio, this is what you get here. So you can see that this electronics is slightly more complicated than the simple counting detector, but our advantage is we are covering a quite a large length of the detection as well as position. So here this divider can be also replaced by using a ratio analysis, and that is again the pulse processing is faster for this ratio analysis. It makes slightly things simpler, and output which is proportional to this position is explaining you about the 2 theta. So there are some other requirements when you are going from a simple detector to this position sensitive detector. So what it is a position accuracy. So what it means, like two nearest neutron arrival positions, how can you differentiate? So that is like how what is the position resolution, the accuracy of the detector, whether they are being treated as a different peak or these peaks are merging. So this again has to be considered while designing the detector. So suppose there is a neutron interaction at this point, a proton and triton. So the triton has losing less energy, so losing energy in the small region. Whereas a proton is 573 kV, it depends now here on the Z value of our ionizing gas. So this even if the neutron is arriving at the same position, here it has a probability of having any isotropic the emission of this proton triton. So between this entire region, it is a charge centroid, uncertainty in the charge centroid. So this itself is a charge centroid, what you call it as the position. So between these two probable positions, this is what determines our intrinsic position uncertainty of in the detector. So how to reduce it is by reduce this range by adding a high Z stopping gas. So if for 1 bar helium-3 this range is nearly 8 centimeters, and if we add a krypton, even increase the helium-3 pressure, as our Z increases, we can reduce it to 3 to 4 millimeter. That one, just here you can just see the graph. If it is a simple helium, we can just see this. It is in the 60 to 80 million. This is showing only proton range, as triton range is usually 1/3 or less than 1/3 of it. So it is going to be a more than 5 to 6 centimeters of this. And for the high Z gases, moreover for polyatomic gases like CF4 or isobutane, it is much lesser, much less. Then why not to use these gases? So we have to add some of these gases. We have to select as per our operation procedures, like what, because all these gases are going to increase our operating voltage of the detector considerably. So usually we are considering either CF4 or krypton as the additive gas, and this you see the chart how at for 6 bar of total detector pressure, here by adding this other argon, krypton, xenon, our centroid value is reduced. I think this is what we are considering. So 3.5 to 1 point. So totally intrinsically we can have at the most 4 millimeter. We have reduced it from 13 millimeter to, sorry, this is 6 bar. So it was at 1 bar helium-3, it was 8 centimeters. We have reduced it to 4 millimeters. So this is how we are going to make our detector with a more better and better having a better position resolution, so that our uncertainty in the collection of data is reduced. So once the detector is made, a position sensitive detector is made, it should be characterized on the using a neutron beam, fine neutron beam at a multipurpose test facility before it is mounted on the actual neutron spectrometer. So it should, as we have seen in the simple detector, we need a sensitivity, detection efficiency, other properties. So along with all those properties, what we need for a position sensitive detector is it should, by every shifting of the position, it should shift, even the peak should shift by the same channels here. So here this is what channels are reflecting in the 2 theta position. So this uniformity of operation, then again all the peaks at all the positions should show you a same neutron intensity. Now here the PST is mounted inside the shielding, and a fine neutron beam falling at one position, so detector is then shifted from one position to other position. Every position is separate from the 10 centimeters. It is a shift of 10 centimeter. Each exposure is nearly 60 seconds. So when your neutron exposure is same, your shift is same. So this is what is a measure of detector uniformity. So this, any non-linearity should not be seen in this output form, so that this will have a perfect, this is a measure of not only detector hardware but as well as your symmetry of the external pulse processing electronics. So any uncertainty does not mean that any one place it is wire is sagging or as such, but it is also a measure of how well your electronics is tuned for equal gain and gain from in the both the branches. Okay. So now this is just a schematic how these PhDs, after a complete confirmation of that okay they are well characterized. They are showing good properties of position, resolution, efficiency, and uniformity of response. Number of PhDs mounted here are, so you can just see that there are 5 PhDs mounted in the angular fashion, so that it is covering the 140 degree of angular range. So this is schematic of powder diffractometer. So all these 5 PhDs mounted on this spectrometer, they are contributing to a total. Considering the overlap, they will give you the total spectrum of 102 degrees to 140 degrees of the scattering angle simultaneously. So this is the gain, whereas if it was a simple small counting detector, it would have taken days together to cover this much sensitive scattering angle from this instrument. So now we have reduced the experimental time, that is reactor beam utility time, as well as you have tailored the position resolution of this detector quite well. Okay, so this is another. So this is another test of the position sensitive detector. Like if you flood the source on the PhDs, so then it should show a uniform response. And then any irregularity seen on this flood pattern will give you either a dust particle or a kink on the wire that will be reflected. So this PhD also should pass through a simple test of uniformity from the flooded source. So this is how your output spectrum will be is compiled from all 5 PhDs, and it has been showing as a single data from 2 degrees to 140 degrees. This is another schematic of of time of flight spectrometer. I will just show you how how the position sensitive detectors are arranged in a multi PhD array, so that the 40 PhDs which are arranged in the angular coverage, so that here you can see they are almost like covering like a two-dimensional PhD. But whereas each PhD is different with the electronics, so when you are measuring a time of flight, so from the sample when neutrons are arriving at certain PhD at certain position and certain time, the time of arrival and the position of the neutron arrival gives you how much energy gain or energy loss has been occurred within the sample. So these are just the multiple number of PhDs assembled here, and just see that all 12 PhDs should have this pulsate spectrum, which is ranging between a similar range. So it is covering only 50 channels in which your all pulsate distribution at the same operating bias voltage. It has been shown that is how this array is needed to have a uniform performance. This is another small angle neutron scattering. You will see all the spectrometers in detail whenever this in the next few lectures. So here they are arranged, 4 PhDs are arranged in a star fashion, so that you are not losing on any information in this angular scattering or in this two-dimensional region also. So here there are 4 PhDs, and all the 4 PhD data can be processed and overlapped, so that your counting statistics is also improved. And here you can see the similar uniformity spectrum collected with the 5 centimeter space. And this position resolution received in this detector is much better than even 4 millimeters. So that's the advantage. Okay. Just a small briefing on how a one-dimensional detector can be again converted into an area detector. So here, rather than having a one resistive wire, you can have three grids, multi-wire grids, having a central one as the avalanche formation grid, and the other two grids are orthogonal to each other, and each of them with the similar charge division will give you X position as well as Y position. So that is how a again the charge division encoding used for this X and Y position. It is same as a linear PLC, but rather than the single wire, you are using here a multi-wire array. So here this anode, multi-wire X upper cathode and lower cathode is contributing to a output which is almost covering your entire area of the detector. So this is a picture how you are seeing mounting three different grids. So this is a central grid. You can see here all fine. There are 120 thin wires mounted on this, and these are the lumped delays which are this here. Rather than using a charge division, here every output is varying by a arrival time. So this is another pulse processing model which can be used for much higher count rate capability, and this is a delay line. Okay, so this is how a delay using the delay line. If your arrival timing is different, this will give you a position as x1, x2, and y1, y2. So a particular point here as an arrival, it can be created within a matrix so that your output pulses will be uh, plotted on the area so that your neutron arrival position in the area detector is then fixed. So here delay line position encoding gives us a very fast pulse processing uh, time so that the count rate capability is also better for these detectors, as well as the position resolution is determined by the wire spacing of the detector. So you can have a very thin, very small wire spacing right up to the 1 to 1.2 centimeter, 1.2 millimeters. So that is wire spacing which we have in this detector which I showed you. And this output of these detectors when they are in the same delay line area detector using a delay line position encoding. When used for a triple axis spectrometer, this is how accurately the beam size it can result in. So this is a 5 centimeter by 5 centimeter of the beam which is being shown here. And you can see the how intensity variation can be very well, very accurately seen here. This is another 3 millimeter by 3 centimeter of the PNR beam, a polarized neutron spectrometer. Again, the high intensity point has to be noted so that you can place the sample within that region. So that is the ultimate use of such detectors. And a large area detectors with a similar structure, nearly 60 to 65 centimeter by 65 centimeter, can be used for the small angle neutron scattering spectrometers. So this is again the linearity plot, the way exactly which we have seen in the 1D PSTs is how you can just shift the detector in front of the beam and get the linearity plot for a 4 millimeter shift with a 2 millimeter dia beam. And at the end of it, I'm showing you just the wide domain of the detectors which we are making here, and right from the small beam monitors till the long 1 meter long position sensitive detectors and its imaging PLCs are been assembled in house, and they have been installed on all the spectrometers, and they are working for quite a good for years together. So that is the success of all the hard work which has been decided by making the detectors. So in case you have any doubt or in case if you have any questions, you may please ask.
Hello. So you heard about detectors from Dr. Shraddha Desai. If you have any questions, you can ask later also at neutroncourse@gmail.com. And the next module begins on Thursday. On Wednesday, 4th of November. The next lecture will be on Introduction to Magnetic Neutron Diffraction by Professor S.M. Yusuf. Please be here at the classroom at 3 o'clock. So it will start. And also remember, there will be one more module, one more set of assignments coming to you. You can download them from Anuvidya for solving and submission. Thanks a lot.